So first, a couple of housekeeping issues. The exam, which I'll hand out next Wednesday for take home. You just missed it? Yeah, it was 30 seconds, it's over. So it's going to be a take home 2-hour. Closed book, closed notes. All right. Any questions on that? Go ahead. Anyone?
Next week, next Wednesday.
Yes. Hand out next Wednesday, bring back to class the following Monday. So, out next Wednesday, back the following Monday. Other things, let's see. The programming assignment number 3 is not out yet. Basically, the way I do these things is I write it all and get a solution, and then I back up to get what I want to give you guys. And I haven't done that backing up part yet. So it will be done today. Let's say tonight. All right. And I have not looked at either your homeworks or the programming assignment from yesterday, although you may have seen the quizzes are graded. Okay, so any questions on those items?
How far up will the exam be covering?
So we will cover through, so let me see.
Is it through next Wednesday, or is it to the end of this week?
That is a very reasonable question. So since we're doing something completely different starting next week, then just check my schedule for a moment and see. Yeah, it'll be through stuff through today. So through chapter, what are we on, 4? Okay.
In terms of, will it be similar to the quizzes, or will there be coding on the exam?
It is, if there were coding, it would be small snippets of code. So, does that answer that question? So quizzes, certainly many of the questions that have been on the quiz could be reasonable questions for the exam. Okay, so we went through Monte Carlo for the last couple of days. And we talked about how we could use Monte Carlo to evaluate the value, either the Q function or the value function for a given policy, right? Part of what we needed. So what assumptions did we have for that? Did we have any, Justin?
Sorry, I missed the first.
For, let's say, for evaluating. So using Monte Carlo to evaluate, this is not very black either. Just a second. Oh my goodness, that is very black. So using the Monte Carlo method to do policy evaluations, right? So given pi, compute either v pi or q pi. Give me kind of roughly how do we do that?
We take, we go through all the states and we check, or we see, or we calculate or we take the sum of the probability times the reward plus the discounted sum of the next state.
Okay, but then back even a second. Where did the reward come from?
Came from the action we took in the state we're in.
Okay, so we take actions.
Yeah.
That's the first thing we do, right? We take actions. For how long?
Until we have a stable policy.
So let's just look for Monte Carlo. For the Monte Carlo, we're going to, where are we going to start? Let's even try that. What state are we going to start in?
Starting state.
It depends, actually. So one way we looked at was Monte Carlo with exploring starts. Right? Exploring starts says we want to try all states, so therefore we'll pick a starting state. Right? So we pick a starting state, and then what do we do?
And then we figure out which action will give us that biggest, or not the best state value. No.
We just follow our policy. Okay? That is, what's the probability if I'm in this state of taking this action? And I take it. And then, right, that's basically our agent takes our action, and then our environment does what?
It gives us a reward and a new state.
Gives us a reward and a state. And as an agent, what do we do then?
We take that new state and we use our policy to get another action.
Victory. So use our policy, take an action, let the environment spit back a new action and reward, and we keep going until
we reach a terminal state.
Until we reach a terminal state. And that is all called what? That sequence of starting at some initial state, taking sequences of actions, getting states, new rewards, keeping going until we get a terminal state. Called
an episode.
An episode, right. So that's an episode, also called a trajectory, right? Because we are traversing through this state space via our actions. So episode or trajectory, and that gives us basically a bunch of state, action, reward values until we get to some final reward. Just as a preview, next chapter, temporal difference learning, we're not going to say we're going to wait until we get to the terminal state, till we get to the end of our episode before we learn anything. We're going to actually start learning step by step by step by step. Okay? And then a little later on, we'll learn there's actually sort of an intermediate. This is like at one end of the extreme, wait till the entire episode. The other end of the extreme is look one step, and there are various intermediate values you can use too. Okay, but Monte Carlo says just wait for the entire thing. Okay? And now we can do this discounting you talked about, right? Figure out basically, okay, for this state, if we were just looking at the state value, we started in this state. What was our reward? This reward plus this discounted plus this discounted plus this discounted all the way to the end. That is a good estimate for this state. What about for this state? Assuming it's a different state, it was the reward after that state and on discounted and so on. And we could do this for every one of our states. If we have a state that's repeated, then we have this question of, do we want to discount the first one or every one? So, Dave, the advantage of the first one. I got this right, I'm sorry. I just looked.
First one.
So this is first visit versus every visit, right?
Yeah.
How do they differ?
Every visit, every single time you reach a state, you do another update, your hypothesis for.
Yeah, basically you're going to look at average returns you got. And for every visit, you're going to say, hey, if you hit it multiple times within the episode or in the trajectory, you're going to count each one of them, right? The first one will have more rewards, the next one will have fewer rewards and fewer rewards and so on. Okay, but in terms of, if we look at the bias, which one is unbiased? Yeah, unbiased. And this guy is biased. In terms of, you look at one episode, it's biased. But over multiple episodes, it approaches unbiased. Okay. And this one is a higher variance, lower variance. And this one requires at least a couple lines of code, and this requires nothing special, because you'll just treat them all the same universally.
Could you go over again why we lose the bias in the long run?
I stated without proof that basically over n episodes, we're approaching n over n plus 1, or the expected value is n over n plus 1 of the true value. And so therefore, as n increases, that gets closer and closer to the desired expected value. Okay. In order to get Q values, we need a Q value for every state and action pair. One way to get that, exploring starts, which basically says, start every episode in a random state and random action, and then follow the policy. And that'll guarantee that we will have, if we have an infinite number of episodes, an infinite number of visits to every state and action pair. Okay. Hard to do in some cases. Hard to enter some sort of random state, depending on what this environment is. And so the other option, Mark, how we can, there you are. What can we do to make sure that we're visiting every state in action?
Use a soft epsilon policy.
Yep, use a soft policy. And in particular, we can use an epsilon soft policy that says we have at least epsilon over a chance of visiting every action. Okay, so if we visit every action, that's great. How do we get to, I guess, we're guaranteed to get to every state, because we'll assume that the environment has, right? If there are states you can't get to, then they sort of might as well not exist. Okay. The problem with that is if we're doing optimization, we're optimizing a soft policy. We're optimizing a policy that does exploration. And if we then want to actually use that, we've now got a policy that is optimized as good as it can be, given that it's doing random action some of the time. So throwing itself off the cliff every so often, you know, walking straight into the big boss's jaws when it wants to go fight, doing stupid things every so often. Would we think we could come up with a better policy than that? It seems like it'd be nice if we could come up with an optimal policy that doesn't have to be stupid some of the time. We knew how to do that with dynamic programming. Because with dynamic programming, since we know what's going on in the environment, we can figure out expected values. But we need some way of kind of doing this exploration. And so we are going to split So we're going to do off policy, both evaluation and optimization. What's often called control, but it's optimization is really, we'll just call it control / optimization. So the idea is we use one policy to evaluate slash optimize, and that we'll call pi, as we always do. But we're going to use a different policy to explore slash interact with the environment. That is, the agent here that's going to be operating with the environment is not pi. It is b. So we have b here, and we've got pi where we're sitting and watching and saying, what can we learn about pi given it's b that's actually operating? We assume we know b. That is, we know its probabilities of taking particular actions in particular states. Okay? So let's come up with this problem. So let's back off. We don't have reinforcement learning anymore. We're going to just look at a simple case of trying to estimate our return with a given problem. So here's our problem. We've got a probability distribution. Okay? So we'll call it, just for the sake of argument, B. And we've got, what were the numbers I used? I don't even know how I'm representing this. Represent it. So we have a 0.25 chance of a reward of 15, 6, 2, and 3. 21, 24, 27. Yeah, good enough. All right. So it happens, we know the exact rewards and the probabilities, but we have this very simplified problem just to try and look what happens and how we can have one policy that we're using to do sampling from to try and figure out something about a different, let's say, policy probability distribution. So this is not a policy. This is just, I've got a problem where I have a equal chance of getting a 15, 6, a 2, or a 3. Okay, and the expected value here? 15, 21, 23, 26 divided by 4, so 6.5. All right, and now I have a different problem. I've got the same rewards, but different probabilities. So this is going to be 1/2. I don't know why I'm switching from decimal to, I don't know, but I am. 1/2, 1/4, 1/8, 1/8. Okay? Clearly our expected value is going to be different. And in fact, our expected value is going to be what? 15 eighths plus 12 eighths plus 2 eighths plus 3 eighths. Is that right? What did I get wrong?
60 over 8. So it's 8.87.
This isn't 15 eighths, clearly. This should be 60 eighths. Okay, thank you. 72, 74, 77 eighths, which is like 9.5, yeah, something like that. Okay, we don't go to even one decimal place. That's a lot for me. Okay, we don't necessarily know what these are. We know that the reward here and the reward here are the same, but let's say we don't actually know what they are. Okay, we're looking inside the box just to make it easier and make sure that this is all going to work out right. Okay, but let's say we didn't know what was in the box, but we knew same boxes, different probabilities for getting those boxes. So now we're going to start taking samples. We're taking samples from our policy that we are exploring with. So if we pick a sample, we have a random chance of getting any one of these. would it be reasonable to just take a bunch of samples here, average them together? If we took a bunch of samples here and averaged them together, what would we get an expectation? I don't know, Allie?
6, is that what you're talking about?
6.5, yeah. We'd like to take a bunch of samples here and average them together in some way and get this instead. So let's say I take a sample and I get a, go ahead.
So is pi like the optimal policy or your current policy?
It's just a different policy. It's a different policy, different probabilities.
So why are we trying to match b and pi? Well,
We're not trying to match b and pi. We're saying this is the one that we're using for distributions. Okay? In the sense of this is the one that's actually going to interact with the environment, right? And get some random reward. But the probabilities that it's using for taking actions are different from this probabilities. This one that's taking actions. So I have got these probabilities for drawing from the boxes that I want to be estimating, but these are the probabilities that I'm actually drawing with. Okay? It's like all I have is a four-sided coin, four-sided die, and this is the only way I can take distributions. Right? I don't have any other way to take distributions. How can I still do this? And the idea is going to be weighting, but let's look at that. So we take one. We happen to get box number 1. We get a 15. If we wanted to weight this, knowing that we are interested in approximating here, would we want to weight this 15 higher or lower? Julius. Julius here. Daniel, Julius not here. He must. Daniel.
Higher.
Higher, right? Because half the time here we're getting a 15. But here only a quarter time. How much higher?
I mean, it might be a function of like the difference in expected value.
Well, we don't know the difference. Unfortunately, we don't know. We're trying to use this to get the expected value. If we had that, we'd be done. We know these, though. So this is known. And this is known. It's the values in here that are unknown. Right? The numbers in there. So we got a 15. How did we get a 15? Because we rolled our dice, four-sided dice. We came up with this one. We took out a 15. How much more likely would we expect to get a 15 following this probability distribution?
You'll be 2 times more.
Yeah, 2 times more likely. Because half the time we would expect half the time we would expect box 1 here, and only a quarter time we expect box 1 here.
I'm sorry, do we know what's in the boxes?
We don't know what's in the boxes, so let's
How do we
make this
box
simpler.
one?
So here's what happens. I had to borrow this from the department secretary because I don't carry coins anymore. So we flip a coin twice. That's 1. And twice, and it comes up 1. Okay? So 0, 0. You know. And we pulled out from our box, and we got a 15. So I'm telling you that's what happened. So we got a 15. Now, I know it was box number 1. And I know that there was a 1/4 chance of that coming out.
Just to clarify, like, so our goal is to find the expected value.
This is our goal. We want to come up with this. We want to come up with the expected, that's what we're trying to come up with, using a Monte Carlo method, because we don't know what's in the boxes. Okay?
As soon as we draw something from a box, do we know that it's always going to be that same thing in that box?
No. No. Otherwise, we'll just keep drawing we'll take 1 from each. This is this is a very simple example, right? Where you can think of what's really happened is we have a random variable in here with some expected value, right? So I'm just making it easier and say, yes, it happens to be 15.
So you're saying that you follow a different policy and then scale it by the ratio of the probabilities to...
The ratio of the probabilities is exactly what we would do. We'd say we'd take 15 and we'd say, this has a probability 1/2, this has only probability 1/4, so this is twice as much as this one. So we'd be times which is 15 times 2. So we overweight that one by 2. Okay. So our current estimate of our expected value for B would just be 15, the average of all the things we've seen. The expected value we'd expect of what we've seen so far for pi is 30, because that's all we've seen. All right, we flip our coin again, shake, 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 flip, flip, flip. It happens to come up the next bin. Okay, probability 1/4. And guess what comes out? A 6. So we get a 6. Overweight it, underweight it, or leave it the same? Okay. The same. Probability 1/4 of having gotten a 6 here. We have a probability of pulling the same thing from here. We should just leave it alone. So we have now a 6. Right? These are our returns we've seen so far. 15 times 2 and 6. What's our current estimate of the expected value for pi?
Pi? 18.
See, so yeah, we got 15 times 2 is 30, and 6 divided by 2 is 18. Current estimate. Everyone with me so far? And correctly, our current estimate for B is lower, right? It's 15 plus 6 divided by 2, or 10. Still too high, but we know what's coming.
When we're doing this, we're not choosing which box, and we're following.
Now, I was flipping. Did you not see me flipping the coin? Okay. I flip again. This one comes up, just proving that it's totally random. Okay? So we get out a 1, right? Is that what in there? A 3? Yes, we get out a 3, exactly. So we get out a 3. Do we need to scale it, Tina?
Yes.
Up or down?
Down.
Down by?
1/2.
Yeah, down by a factor of 2.
Oh, sorry,
Yeah, because basically times 1/8 over 1/4, right? So 1.5. So now we've got a 1.5 in here.
Shouldn't
Nick.
the bottom one still be a 3? Or, so, oh, never mind. That's for EPOP.
Yeah, this is all pi.
Okay.
Up here, what have we got? We've gotten a 15 and a 6 and a 3. Yes?
So if you just randomly roll 3, how do you know what box it is in?
I'm rolling a box.
Oh, are you rolling a box?
I'm rolling a box. Yeah, I'm rolling a 1 through 4 that tells me which box to do.
Okay, and that box gives you
That box gives me a value. Yep.
So just to kind of like recap what's going on here.
Yep.
We're in a state where we want to avoid the situation where we don't really figure out about all of our actions to do our like read or only following our policy. So we try everything at some random order, and we just scale up to the ratios of our own policy.
We haven't talked about the random order yet, so we do have some restrictions on what this B policy is going to be. But basically what will happen is we're going to follow a different policy, and so therefore when we get rewards, we will need to weight them, depending on how likely or unlikely that a policy is.
So my next question is that...
I'm sorry, not the policy. How likely or unlikely that episode was, that trajectory.
So then these values like 15, 6, 3, 2, are those just the immediate reward or like the value of the next state? The estimate of the value plus the reward? Like the reward plus the discounted? Like is it...
It'll be the total reward.
It's total.
We will get into that in just a moment. Yeah. So, you had a question, Nick? No. Okay. And then the final one, let's just look. We get, what did I roll? Would you guess? It depends if I'm 0-based or 1-based, right? I happen to roll this one, right? And so I didn't roll a 2. I rolled a third box. I pick out, I get a 2. Our average happens to exactly hit the expected value. Here, 2, we will scale down because we are less likely to have chosen the box than the Monte Carlo is to have actually used that box. And so 2 times equals 1. 15.2, 21 point, no, sorry. It's not 15.2. 30, 6, 37, 38.5 divided by 4 is around 9.625. So the average is around 9.5 as you expect. Now, did we choose this exactly to try and make this work by we just got lucky and hit every box? Yes, we got lucky in every box. If we were actually using random numbers and choosing according to these probabilities and multiplying by the scaling factors, we would have still ended up, we would have approached our estimate.
One thing I'm confused about is, like, in this case, it seems like we would want to hit every box, so why don't we just choose to do that rather than, like, making it random? Because you're, like, rolling a dice and then choosing a box, or why not? Like, can you just be like, oh, do this action, so you can see what happens?
Not necessarily. So for instance, I'm interacting with a non-deterministic environment, which is giving me a reward. And so I can only go and see what happens, right? I don't really know how to move from state to state and all so on. So this, by the way, is called importance sampling. And this is not anything that's specific to reinforcement learning. All right, this is just a way of dealing with sampling from one distribution and applying that to another distribution. So does this make sense? All right. I'm going to make another little chart here. So let's see, we've got importance sampling. I'm going to call this ordinary importance sampling, which is what this is. Right? So basically, just scale, take the averages. So we just take the sum of the scaled values and divide by the number, right, of the scaled values. It's the average. This is unbiased. But can have high variance because of the fact that these scaling ratios can be arbitrarily large, right? It just depends on what the ratio is between the probability here and the probability here. So you've got something that's very unlikely here and very likely here. You could have a huge ratio there. So large bias. Sorry, no bias, large variance. In fact, as the book goes through and describes, in some cases, when we're looking at episodes, this could be infinite, which is pretty large. We're going to also introduce weighted importance sampling. And I'll do that with this example in just a moment. Weighted importance sampling has lower variance, finite, which is kind of nice. But what we give up is it's biased. In terms of taking one sample, right? When we take one sample in the way we've described here, one sample is unbiased. Okay, that is, when you take a sample, an expectation, it is the expected value according to pi. When you take one sample in this weighted importance sampling, it is actually has an expected value of b. But as you take more and more of them, they approach b and move towards pi, which sounds kind of similar, doesn't it? It sounds exactly like the bias and variance we were talking about in terms of every visit and first visit. So here, but in the limit, approaches so starts out as the expected value of b, but ends up approaching expected value of pi.
So when you say weighted importance sampling, you mean?
We haven't talked about what it is yet.
Okay.
I'm about to give it to you. I'm telling you where we're going with it and why we're going somewhere with it. Now I'll give you the formula. So this equals the sum of rho of x, just whatever our scaling factor is for that particular one. Instead of dividing by the number of scaled factors, we divide by the sum of rho sub x. So let me just show it to you, and then we'll observe that the variance is lower, we'll observe that it's biased, and we'll observe that it tends to approach the correct expectation. So we'll take the same values. So this one was ordinary, and this one is going to be weighted. So this is weighted. Important sampling. Take same values. We get a 15. We take 15 times 2, just as we did before, but our initial estimate is going to be that divided by 2. Okay, so this is the estimate after one step, which equals 15, which is exactly in expectation E sub b, right? Because basically we just cancel the 2 and the 2, and it's just we drew from b according to b's probability distribution. What do we expect? That we would get whatever the expected value is.
Where does the bottom 2 come?
The bottom 2 is that we're taking the sum of our scaling factors. So our scaling factor is 2. The sum of our scaling factors so far is 2. Now we choose box 1, we get out a 6, we leave that alone, and so our new estimate is going to be 15 times 2 plus 6 times 1 over 2 plus 1. Okay, so 36 divided by 3, 12. Hey, makes sense, I guess. We're maybe approaching that. Our third estimate is 15 times 2 plus 6 times 1 plus, what is it? 3 times 1/2 all over 2 plus 1 plus 1/2. 36, 37.5 divided by 3.5.
39. Oh, no, 1.5. The 3 takes it back.
Okay, 37.5 divided by 3.5, so that's just over 10. So it's 10 point, I'm going to just throw in a 2. I don't know whether it's 2, but it's something. And then our fourth estimate, 15 times 2 plus 6 times 1 plus 3 times 1/2 plus 2 times 1/2 over, and again, instead of 4, it's over 2 plus 1 plus 1/2 plus 1/2, which funnily enough actually is 4. How handy. So we now have the same, what was it, 9 point something, 9 point, what were we saying, 9.5. Whatever we said it was, we'll say it is. Okay, so that's weighted importance sampling. Shannon, you have a question.
Can you define row?
Row is the probability of x in pi over the probability of x in b. So we've got some x. Okay.
So, is the bias demonstrated in this example, or?
The bias is demonstrated because of the fact that the first item you select, right? Basically, when you make one sample, the two ratios are going to cancel, and so you're left just with a sample from B unscaled. When you sample from B unscaled, you're getting the expected value of B. You know, the expected value of taking a sample from B is the expected value of B.
Well, that's just the value of one sample from B. It's not the expected value of samples from B. It's more so biased by just whatever value you got.
The expected value of that random variable of choosing from B using its probability distribution is the expected value of that, right?
But we don't have an expectation. We only have a single value. There's no expectation there.
Well, we have in expectation, that value is the expected value, right?
Okay.
It's a random variable, that value. And we'll just approximate it by doing lots and lots of different samples. Any individual sample, if you were to look at it by itself, since we just cancel those two, would just be an expected value of B. So, but as you put them all together, you end up with the expected value of pi.
Both of these different ways of sampling both seem to be like they're fixed by like doing a lot of samples. So like how do you choose which one to use? So I feel like the variance from the ordinary one would also go away if you went to the limit.
Yeah, unfortunately, given that you can have infinite variance, it doesn't go down very much. So in practice, you want to use weighted importance sampling. Okay, so that you for sure want to do, and you probably want to do every visit as well if you're looking at that form of bias and variance. We're going to look at one other way we can reduce the variance in a little bit later, okay? Which has the advantage that it is unbiased, but still has fewer sources of the variance. Okay, but first we have to talk about applying this to an episode and to the Monte Carlo. Okay.
So it seems that in like certain probability distributions, you wouldn't necessarily get a similar output like this.
Well, so my proof is I picked these numbers randomly and it worked, right? I don't think that's the case. So this should, in the limit, always give you the correct estimate of expected value. Yeah, think about that. Mark.
Was the variance tending to being able or being bounded? Is that due to the ratio of B and pi?
That's due to the ratio of B and pi, and I should really be more clear. Large could be. So as we're going into these episodes, we're going to have, we'll look at it in a second, but we have multiple ratios that we're going to have to look at. Basically, every time we look at an action that is chosen, there's a probability of B choosing it, and there's a probability of pi choosing it, and we're going to have to take that ratio. And then the next action, the same thing, the next action, the same thing. So we have a potentially large number of these ratios multiplied together. Okay.
It's the reason why in practice we use weighted, and I guess also for every visit, that we can't change the bias necessarily, but if we run more episodes, we can get, other way around. We can't change the variance, but we can reduce the bias as we run more episodes because the limit will be the same.
The limit will be the same, and we will turn out a lot better, and we will converge or approach what we want sooner with our weighted endpoint sampling.
Is it that, like, we have control over that element, or is there a way that we can reduce the variance too, without, I don't know how to express it.
So
I guess it's just
I would just
inherent in the way that you're sampling.
there.
The variance is gonna be big, so is there like something we can do to counteract that?
Oh no, there's nothing we can particularly do to counteract that variance, except for the approach that we were going to talk about at the end of class today, which is a modification to the ordinary that will be useful. Let's look at applying this to policies in reinforcement learning. Okay, so let's say you are trying to learn to play a video game, all right? But you're not actually playing it. You're watching over the shoulder of someone else who is playing. Is it possible to learn something? Yeah, you can possibly learn a lot. You may have different strategies that you use in your play than the person you're watching does. But when the person does what you would have done, that can be very useful to come up with, to see what sort of rewards they might get from doing that. So that's kind of part of the idea of this. So if we've got our policy B, let's look at our example. So let's say we've got S and T, and we've got two actions. Go ahead.
Okay, so just using the same analogy, like if you are going to watch someone play it and try to learn from that, why don't you just go ahead and try it yourself?
Why not just try it yourself? There's a variety of different answers to that. So one answer might be let's see if I can split. So maybe you're not watching yourself. Maybe you are remembering what you did yesterday. And since yesterday, you've made some adjustments to how you play. Okay? And so therefore, the policy you had from yesterday is not the same thing from the policy you had today. But you would like to use that information from yesterday to improve your policy today. So you think back and you say, I can't quite directly use that, but I do, of course, know all my probabilities for every action given every state. And therefore, I can weight those to calculate for my new policy what its value function should be. And from that, then improve it. Does that make sense? That's one example.
It could also be that, like, by observing someone play the video game, that they're reaching states that you didn't reach during your gameplay, and you can, like, learn from those situations that you haven't experienced.
Oh my gosh, that's a good idea. So in fact, didn't we motivate this from saying, what if I've got like I'm trying to learn an optimal policy. Optimal policies don't do exploration, right? It'd be nice to go ahead and have someone exploring on my behalf, right? Here's the reason. He's paying the quarters and dying, and I'm not, right? So, yeah, perfect point is if we have some sort of an epsilon soft policy that is doing the exploring, it's out there taking the arrows in the back with the poor. And we just, yeah. So anyway, here we go. So we've got this, we've got, and we've got a reward, let's say, of 3. And here we've got a reward of 3. So at 100%, right? So we've got a terminal state. we've got a state where if you take action A1, you stay in that state, and if you take action 2, you go to the terminal state. And in each case, you get a reward of 3. I'm going to make my math simpler, and we'll just make it a 1. Okay? So however long you can make the episode last, you get that many units of reward. And we have 2 policies. We have a B policy, which says in S, A1, 50%, and A2, 50%. And we have a policy pi, which says in state S, A1 is 90%, and A2 is 10%. All right? Which would we expect to have a higher value for state S? Nick?
You would expect pi to have.
Yeah, sure, because we're more likely to have longer episodes. Okay. We run via policy B, and here's what we get. S, A1, 1, S, A1, 1, S, A2, 1. Could that be a valid trajectory that we get from that? Okay. No discounting, what's the reward?
No discounting, it'd be 3.
Be 3. And now we've got to scale this. Do we want to scale this up or down? Up sounds good because we know we want the value of this according to pi. Right? We know the pi of S should be greater than BV of S. So it makes sense to scale. In fact, I thought before I worked out this that it would go up. It actually doesn't. We'll see why. Okay. Yeah.
But don't you want to scale the individual actions? Not
We're going to scale the individual actions. That's what we're going to do. Oh, and let's just do first visit to make life easier. So we're going to just do first visit. So we're going to just look at this date. Okay? So the probability, what's the probability of this trajectory in B? We started in S. And let's just kind of look at the probabilities that got us from various places. We have, let me make plenty of room here. We have B of A1 given S. Would you agree? So we started in state S. What's the probability that we took action A1? And then, what's the probability that we got to S given A1 and S? I'm going to ignore the reward here, okay? Because I don't care about the reward. I care about where we traversed. So we can think of a 3-argument version of P. I think, in fact, you guys even did maybe an example of this, something in the book. Okay? And I'm going to just multiply all these together. Times now the probability of A1 given S, times again returning to state A. So that takes care of, we chose this action, and then the probability of choosing A2, and then the probability of ending up in T given A2, comma S. Would you agree with that?
Yes.
Okay. And if we wanted to change this out so this is the probability of our trajectory with policy B. If we want to change it to pi, we swap out B with pi, right? Pi of A1 given S, pi of A1 given S, and pi of A2 given S. Okay? So we're going to define rho to be it would have been easier if I'd written this over here, and then we kind of said this one and this one, but it's this one or this one, right? So we're going to have basically on the top pi of A1 given S, and I'm going to just write these next to each other. Pi of A1 given S, pi of A2 given S. And on the bottom, actually we're not done. We still have to put our p's, but I'm going to get back to those. B of A1 given S, B of A1 given S, B of A2 given S. And then we still got our p's. P of S given A1 and S divided by P of S, A1 comma S. All right, so we have our 3 P's here and our 3 B's here. I'm not bothering writing them because I'm going to cancel them. Right? Do we agree with that? So we can look at the probability of this trajectory happening given pi, the probability of it happening given b, the ratio between those two, and the environment cancels out. And all we're left with is the ratio between each of the choices of taking a given action in a given state. And now we can just compute these values and scale our reward. So the value is going to be, right, rho equals 0.9 times 0.1 over 0.5 times 0.5 times 0.5. Yes? And so that's going to be, I'm going to call this 2, and this 2, and this 1/5. Right? So this is approximately 4/5. But it's clearly less than 1. So we're going to take this 3 that we got here, and we're going to scale it by 4/5. How can that possibly be right? Arun?
Because if you did pi, you'd expect to get more 1, so this trajectory is quite.
This is an unlikely trajectory. Exactly. This is not a very likely trajectory for pi. Pi likes long trajectories. Those longer ones, we're going to overweight. The shorter ones, we'll underweight. That's how this is going to work. Does that make sense? Okay. That's basically what we're going to do. We're going to take, now, anything more we need to look at here? I don't think so. I don't think there's a lot to look at. Let's, I guess let me put the actual equation up. Let me not. Let me put the code up. I think that's more interesting for right now.
Another small clarification.
Yep.
Those things that we had in the box were more like total reward for an episode.
Those are more like total reward for an episode, and those are more like random variables, which are the total rewards, right, as opposed to known values. So we're drawing from some probability distribution dependent on the environment, dependent on really the episode and the environment, right,
Yeah.
the interaction between the two. Okay, so here's what we're going to do. It'd be nice if we could see this. It turns out, make sure the video cord is plugged in. All right, so we're trying to estimate. So we initialize our Q values to random values. Sorry, let's even back up a second. What do we need for B? There is an important thing that we need for B in order to ensure that our ratio is defined. That is, when we've got some given pi of s comma a over b of s comma a, is it possible the pi is 0? Sure, the policy could have tried something that we never would. Is it possible that b is 0? Exactly, not good, right? So we want coverage. That is, if pi of SA is greater than 0, that implies b of SA is greater than 0. Okay, we want this actually not because we're going to get undefined values. How is it we would avoid getting an undefined value? Kaki. Why am I saying we'd never get this undefined value in one of our trajectories?
B is 0.
If, let's say there is an S and A such that B of SA is 0.
Then that also has to be 0.
Could be. Let's go back to the trajectory. Shannon.
It's just never going to happen.
It's never going to happen. If we would never have chosen S given A, sorry, these are backwards, I apologize. If we've never chosen A given S, then we never got there in the trajectory, and so it's never going to be using this multiplier. So it's not that that's have to actually be undefined, it's that we want to make sure everything that pi would try, B will eventually try. Otherwise, we're not going to be able to correctly evaluate some of the things that pi would do.
So B should be at least as exploratory as possible.
Yep. Yeah. B can do everything that pi can do, but B can do it better. Well, not better, but more likely. I mean, yeah, more. It can do at least as many things as at least exploratory as B. And we really probably want it to be epsilon soft. We want it to be exploring everything because we need, in fact, we really need that because in order to evaluate Q of SA for all S and all A, we need to make sure we're exploring. Okay. So we generate an episode using B. We go ahead and this is just calculating our total return. So discounted return. This gives us our denominator, our sum of our weights. We update Q based on our ratio. We're working from the back towards the front. Okay? So if we look at if we have an episode of length 3, that'll actually give us 3 different estimates, 3 different runs through the loop here, right? Assuming we're doing every visit in this case. So because we don't have any special check in here. So we're going to go from the end, the very last thing we did, and then the next to last, and then the next to last. And we have to, of course, multiply our weight ratio each time, that pi over B. So this is our weighting factor we've been looking at, right? This is the weighted importance sampling. This is what we're accustomed to. This is what we're accustomed to. This is just building up that row over time, and this is building up the denominator. There's a key thing here. So while W not equal 0, Josh, why do we stop looping if W becomes 0, and in what case would W become 0?
Maybe we stop updating because, or when W equals 0, then the updates stop doing anything.
It is certainly true. That's a good reason to, so that is a reason to stop. Because once W is 0, it stays 0, and then this is not going to do anything, and so it's worthless. So from a higher level, when would W become 0?
When you can converge it.
So this W is just for one episode. This is not convergence. This is just strictly this pi over b ratio, this row ratio that we multiply for the length of the episode. And then when we get to the next episode, we throw it away and start again. So how could a multiplication of pi sk ak given sk over b of ak given sk, how can that equal 0? Right, what would cause that?
Either if like b gets really big, or if just pi goes to 0.
Okay, so pi, let's say pi is equal 0. And so what would that mean? Why was pi 0?
It's not being rewards anymore.
No, pi is 0 because our policy says in this state we never take this action. So the behavior policy took an action in a state, and we're looking at, we're going like, I would never do that. And if you would never do it, then you don't care about the rewards you get from it. That's almost true. Okay.
That feels problematic. That feels to go against like the nature of why we're doing the exploration.
That's a good point. I agree with you. So if we were looking at estimating the value function, what I just said would be correct. But we're not looking at estimating the value function. What do we estimate? We're not looking at estimating the state value function. We're looking at estimating the action value function. And there's a neat thing about action value function, and that is when we say Q of S comma A, this is, with respect to pi, take this action in this state, regardless of whether pi would or not. Take this action in this state and then follow pi. So therefore, if we look at a trajectory, right? State, action, reward, state, action, reward, state, action, reward, state, action. This is B. At some point, like let's say here, pi never would do this. Okay? If pi would never do this, the prefix of this trajectory is useless for us. Because if we're trying to estimate what would happen if we took this action in this state and then followed pi, it's not possible because we'd never get past here.
But in order
Daniel.
to avoid that, why don't you just impose another condition saying if pi equals 0, then b equals 0?
Well, because then it wouldn't explore. And we want it to explore, right? As we can point out. So we get rid of this part at the top. If this is the last never would do this, right? So there's all the rest of this matches pi in the sense that there's a non-zero chance that pi could do any of these things, right? You imagine I'm watching someone play the arcade and it's like all of a sudden they take the machine and throw it over on its side. It's like, I would never do that. Oh, but you did get a good score. No, but I would never do that, right? So we just don't even bother. What would happen? Yeah.
So for clarification, but like you can still learn from the value of that. So next time, like after updating your policy, next time you might like struggle.
Well, here's what we do. We learn from everything from that action on, including that action. Okay? So we have a bunch of actions that we could have taken. We're estimating all these Q of A's, 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 and this one. I wouldn't have taken that action, but what'd you get for that? What was your reward for that? And so that tells me, even though I wouldn't choose A, if I did choose A from this state and then did things I would do, what's my reward? Okay? So therefore, as we look here, when I am estimating the first time through this loop, no weighting happens. Because W starts out as 1, and C becomes 1, and this is just 1. So I'm actually always one step behind in updating these pies. Because when I'm looking at my final reward, just before I terminate, I don't want to discount it. Okay? Because my question is, what would happen if I'm in the next to the last state and I take this action? What would I get? And then I'll follow the policy from then on. But the first action you take, we don't try and adjust for every one of these subsequences of this. Right? So if we're doing this to calculate for this state, if we're doing this to calculate this state, this one, this state, and our final one. Okay. Garrett.
I feel like we're throwing out a lot of our episode data for the Monte Carlo when we do this, especially if our pi is like a deterministic policy where it's probability 1 in one place and 0 everywhere else. How does that affect how many episodes we have to do to learn?
Yeah, that's a problem. It's a problem. Yes, indeed. So, and often what we're going to be doing is, in fact, optimizing a deterministic policy. And so really, the only interesting thing that's happening is the one action that happens before you start locking into following that deterministic policy. Okay? And the closer your policy that you're behaving under and that or the target, the more that it's useful. So it's better if I am using a behavior policy from yesterday with a slightly improved policy today, because most of us, we're mostly the same. And actually, ideally, it's a epsilon. Yesterday's would be an epsilon soft version.
I was going to ask, like, what happens if you got two things that you wouldn't do, like, back to back?
Two things I wouldn't do. I basically, from the end of the episode, I keep going until I find something I wouldn't do. And I throw away everything before that. Okay? Because if I get to one I would never do, it affects, from them before. You had a question, Austin?
So I guess the question is, what advantage does this method have over the exploration from epsilon soft? Or
like an epsilon greedy?
Yeah, epsilon greedy, like the soft policy, right?
The problem with that is when I'm done, I have a policy that does random shit.
Right.
It's as good as it can get given it does random shit. But an even better policy would be don't do random shit.
So this is just like a way to use the epsilon soft by making it your...
By making it my behavior policy. Yeah. So basically we're trying to come up with pi star. And this is going to be a real pi star, right? Not a pi star among all epsilon soft policies, a complete pi star. And what we can do is, again, generate episodes, update the Q policies, update pi to take the argmax. No difference to what we've been doing before. And we're working from the bottom of the episode back to the top, right? The end of the episode back to the beginning of the episode. If at any point in time we take an action, or an action was chosen that we wouldn't have taken, then bail out because the rest of it we don't care about.
Alright, you just do it on policy, and then like when it converges, you just get rid of epsilon.
I'll give you an example. Here's our problem. It's in relief, sort of. So this is a cliff. And if I step off the cliff, I die. Okay? So I'm trying to get from here to here. Okay? If I've got a deterministic policy, here's the best policy. So we'll just do what I did. Start here and go forward and walk and walk and walk and walk. I'm trying to do it as quick as possible because I get negative ones for every step until I go. I make it. That's a deterministic optimal policy. If I flip a coin every step I take and randomly, most of the time we'll go straight forward in this case, but randomly go left, right, bottom, or top, you know what I mean? Then I don't want to be this close to the cliff. In order to have the best chance to increase my reward, I'm going to walk away from the cliff and stay away from the cliff and walk over here. And knowing sometimes I go like this, and sometimes I go back, and stuff like that, but I'm not falling off the cliff, very likely. And then when I get to the end, go back over here. Can you see that's a better policy if I'm sometimes doing random shit? Yes?
No, my question.
Oh, whose question was it? Oh, sorry. And does that make sense? And so therefore, if I optimize my epsilon greedy, my epsilon greedy policy is going to learn to do this, and then if I take on off my epsilon stuff, I'm still not got an optimal policy. Because I had to learn to be careful to try and work around my randomness.
In that analogy, what represents like, the distance between you?
It's going to depend on what the balance between how much it costs to go over here, how much it costs to jump off the cliff, how big my epsilon is. Right? If I have a 50% chance of going in a random action, I'm going to try to be farther away than if I have 0.0001.
So it's just based on like, past experience.
Yeah, it's going to be based on whatever gives me the Bellman equation for, in a case like this room, it worked out, I went as far as I could, I can't go any farther.
So does that also mean that like for the epsilon policy, you get like more robustness like with the optimal policy, kind of, because it reduces the noise or like unexpected.
If you had so it's unclear that it'll help with noisiness in the environment. It certainly helps with noisiness in the policy. If for some reason, right, as you know, if you walk near a cliff, be really careful, because if you accidentally go to the right, you will fall, and that's a big negative reward. But there's a separation sort of from the policy and the environment. As well, if the cliff crumbles, then that's a problem. But that's an environment problem. And never happened to me before. Every time I tried this walk, it never crumbled, so I was okay. But maybe I was just lucky.
One last clarification on why the ordinary sampling gives this infinite variance. That's just a question. Like, why is it infinite variance?
The infinite variance, there's a good discussion of this in the book. What basically happened, in fact, I think the example is not dissimilar from this. Oh, the difference they have is, I think they make this as 0. So you basically got a reward of 1, no matter how long your episode is. But the longer your episode, the more you're multiplying by that ratio, right? So you're going to multiply a 5 episode by 5 and a 10 episode by, you're going to multiply a 5 episode by about 2 to the 5th. Right, in this case, 0.9 over 0.5, and a 10 episode by 2 to the 10th. And so they just get so huge that the variance ends up infinite.
I'm sorry, where does those factors come from?
These come from, remember how we had 0.9 times 0.9 times 0.1 over 0.5 times 0.5 times 0.5. I'm calling this a round 2. And so if we look at the length of the episode, it's basically, if it's a length n, it's about 2 to the n factor there.
I see. So the weighted importance sampling just kind of normalizes against our Rhodes.
Yes. Yep. Yep. All right. So there is one other section I was going to talk about, which is the per decision importance sampling. It's a slight modification. I will talk about that on Monday. It is part of your reading, and it does count as part of the exam because it's still part of chapter 4. Okay? And as well as this programming assignment, to the extent that it's still part of Monte Carlo and it's still fair game for the exam team. So it's all part of up through chapter 4. I'll be in the cafe till 3:30, and then I'll be in my office till probably around 6:30.